just start charging this battery in case I need it again. Okay, so I think we got that. Everybody good on that problem? You're seeing the level of the kind of question. Like a lot of these questions are just one line long. They're not that long. So, you know, I'm not asking. The stuff that's weird, or maybe you haven't seen it before, tends to be usually going to be shorter stuff. Okay, let's do some other problems here. I'm going to jump around a little more. Let's go to number 4. Okay. Not counting rearrangements of blocks. How many JCFs, or canonical forms, are possible for an 11 by 11 matrix okay, then you have to be quiet. With eigenvalues, lambda equals 2, 2, 2, 2, 6, 6, 6, 6, 8, 8, 8. Question. How many? Pardon? Oh, I'm sorry. This is not part of that. I just wasn't even thinking.
Actually, you just put 4 6s in a row. 4 6s means nothing.
Okay, good.
No, but my phone number has 606.
That's funny. Okay. Does everybody have the answer yet?
Oh, yeah.
Do you have the answer, Christine? I know you have it. But you can't tell.
Oh!
Who has the answer?
Wait, shush.
Quick. Is it 75? No, you using the 75?
Is it 105?
All right, we need some more votes.
Yes,
Not much, no consistency. Okay, what's your answer? Yeah, 35, we have 75. The order of the blocks doesn't matter. So if I put all the Jordan blocks with lambda equal to 2 first, and then all the ones with 6, and then all the ones with 8, regardless of the order,
75.
those are all viewed to be the same. Okay, we have 2 votes for 75 now. Joseph?
75.
Yeah? Mark? No answer? Okay, how do you do this? Basically you have to take the different lambdas and work on them independently. You have to figure them out separately. So, what do you want to change it to? Okay, so we're getting a lot of votes for 75. The point is that you have lambda equals 2 showing up 4 times. That means the algebraic multiplicity is 4. The number of Jordan blocks, however, could be anything from 1, 2, 3, or 4. The number of blocks, remember, that's the geometric multiplicity. So the m sub lambda, right, that's the algebraic multiplicity. So for lambda equals to 2, that's 4. But the dimension of the eigenspace, right, could be 1, 2, 3, or 4. And so then you can start just writing down what are the possible sizes of the blocks. So you could have one 4 by 4 block. That would be a geometric multiplicity of 1. Or you could have a 3 by 3 block and a 1 by 1 block. Or you could have 2 2 by 2 blocks. And 2 1 1 would be the case of a 3-dimensional eigenspace. And then the last case is this one. So you see there's 1, 2, 3, 4, 5 cases there. So you have 5 different possibilities here. Similarly 5 here. And then there's 3 here. And because these are operating independently of each other, you multiply those possibilities together to get the final answer. Does this make sense? Okay. So you might want to go back and review those problems where I say things like, oh, suppose you have a 9 by 9 matrix, and you have a certain eigenvalue of a certain multiplicity, You know, so what if I give you a matrix whose eigenvalues are, let's say it's an 8 by 8 matrix with those eigenvalues, right? If I say something like a minus lambda I to the 5th power is 0, now I'm going to ask you, how many Jordan canonical forms could this matrix have? So what you have to think about is, do you remember the cycles? So not only how many cycles, that's one thing, how many blocks are there, but also how long are those blocks. So something like this, remember you start over here with a vector that you're going to choose, and then you work your way along the cycle, a minus lambda I times v, a minus lambda I squared times v, and eventually the last one would be a minus lambda I to the 4th times v. So that's a cycle of 1, 2, 3, 4, 5, length 5. So you would therefore have to have a 5 by 5 block, because you have a cycle of length 5. See, if this may, okay, that would be, okay, let me just add, a minus lambda I to the 4th is not 0. If I specifically say that, which I should, I know I did on the midterm, then you know there's a vector that will survive all of these steps, right? So you'll get 1, 2, 3, 4, 5 non-zero vectors in the cycle. So then you know you have to have a 5 by 5 block. And you cannot have blocks larger than 5 by 5. So then what are your possibilities if the whole thing is 8 by 8? Well, you could have 5 and 3, or 5, 2, 1, or 5, 1, 1, 1. Up to rearrangements of blocks, that's it. When I say rearrangements of the blocks, that just means, okay, you don't have to put the 5 by 5 block first. You could put it in a different spot. Question?
If you didn't put that to the 4th power isn't 0, does that mean you can do like a 4 and 4?
Well, if I leave this off, then I'm not really being clear that there has to be a 5 by 5 block. So then I would have to think about things like, yeah, 4 and 4.
So you'd be 8.
You get a whole lot more things here. Yeah, Christine?
So for this problem, there was one, like when I was doing my possible sizes, there's one I missed.
Okay.
Is there a way to check this out on that?
You mean you missed one of these things over here?
Yeah.
You need to be really careful how you write them down. You always want to put the bigger numbers first, and tend to work from bigger to smaller. So, you know, if you have numbers that are bigger than 1 over here, you want to then break them down, leaving the stuff to the left the same. Yeah, it can be a little tricky. I've seen people miss those before, especially if it's a big number. It's like 15 by 15 matrices.
Is there a
or something.
formula?
Yeah, there is a form. These are the number of partitions of n is a well-established thing that's been studied a lot, but it's not a nice formula that is closed form. So I can't just write down a formula for you. But if you gave me a number, I'd be able to use the formula that's known to tell you how many partitions there are. If that makes sense.
Does that formula, that one, can you include that part? Like where you can exclude all things higher than a certain number?
I know that is also known, that work has also been done, but that gets even more complicated. So it's not something that I want you worrying about for tomorrow. Yeah, no, that's a very, very popular thing to study. Okay, let's see. Let me give you another example. Is everybody doing okay so far? With the what? With which size would be the correct one? Or which of these would be the correct one? Well, you have to know, basically, what do you do when you got these choices presented to you? You do a couple of things. First of all, you figure out how many true eigenvectors do you have? And that might already answer the question for you. Now, in this case, if there were two true eigenvectors, well, then that means there's two blocks and you'd have a couple of choices. But if there was only one true eigenvector, it would have to be that one. If there were three, it would have to be this one, and if there were four, it would have to be this one. So the number of true eigenvectors, in other words, the dimension of this eigenspace, will often reduce your choices. And then once you're down to analyzing something like 3,1 versus 2,2, now you're interested in looking at the sizes of the blocks. Could there be a 3 by 3 block? So if I tell you that, you know, a minus lambda I squared is not 0, then you say, oh yeah, so there is a 3 by 3 block, so I must be in this case. It's that sort of thing. Okay, let's try another example off of the review sheet here. This is actually the first one. Let's solve x1 prime equals negative 3x1 minus x2 minus 2x3, and x2 prime equals x1 plus x3, and x3 prime equals x1. There are, when we're thinking about, I mentioned this earlier, when we're thinking about applications, probably the main applications that we've talked about are this one here, systems of differential equation. So these are applied problems. On the exam that I wrote last year, I actually made a section on the final that was applied problems. And they were all just the applied problems. I put them together. I'm not sure if I'll do that this time around or not. But you should know how to solve these applied problems. Here's one example of it. Another one is Markov processes. Oh, right, another point. I will be prepared, if anybody needs, okay, this is a no calculator exam, right? But if you need something calculated, say you need the inverse of a 3 by 3 matrix or something like that, you can come on up front. I'll be sitting up there. You can just come on up and ask me. I'll do some calculations for you. That might be an issue for you. You'll have to, we'll talk about that. I think I don't have to handle it. So yeah, that's a possibility. Because like on this Markov processes, you have to find the inverse of a 3 by 3 if it's a three state problem. Then we have least squares approximation. Oh, I meant to review that while we were talking about it earlier. Does everybody remember the formula for the x naught vector? This is the vector that holds the scalars of the either line or parabola. I guess was the two that we did. A star times A what? Inverse? Times what? Okay. So everybody should make sure you know that.
And then the error is the magnitude of y minus a. What is y minus a? Yeah? Or just y minus a?
Square.
Square, I said.
Sorry. So, those are a couple of things that are good to know in the context of least squared. Was there another application that I'm not thinking of?
I feel like there were three before with least squares. Wait.
That's this one. Does anybody have a sample final with them?
Wait, is this chapter? What chapter is this?
Well,
What
this
chapter was
is,
systems of belief?
that was chapter 7. This is chapter 7. This is chapter 5, and this is actually chapter 6.
So
I'm trying to think,
I think it mentions it in chapter 5.
This one's a final info?
No, I'm wondering, does anybody have the actual sample final?
Computations of matrices.
Oh, is that what it is?
Yeah.
Is that all I was getting at?
Yeah.
Okay.
computations.
All right. Well, computations of matrices. That just means diagonalization. That's fine. Computing high powers of matrices, things like that, by diagonalizing them.
Were
Yeah.
you thinking of the transformation with geometry?
Oh yeah. Yes, that's what I was thinking of. Oh yes, and that is one of my favorite. Did I end up asking that on the second test?
Yes.
Yes.
You had 3 dimensional.
No, I did a 2-dimensional one. I did a 3-dimensional one in the review section.
No, you did.
Huh?
You did on the second.
A two-dimensional one.
Oh, yeah, two.
It was two-dimensional. What I'm saying is, I think I did a three-dimensional one in the review session for the test, but then a two-dimensional one on the test.
Yeah,
Yeah.
you were nice to us.
I was nice to you, but that was back in March.
You should be
Okay,
nice.
so,
Wasn't that just like
geometric,
That was like 2 weeks ago.
oh, I guess that was just 2 weeks ago. Geometric transformations.
It literally was.
I love this stuff. Actually, all of these are good. Even though I'm a pure mathematician, I like all of it. Every time I teach this class, I get more excited about the fact that this all has nice applications. So you should be ready for any of this, any of these things. I stayed away from systems of DEs before on the test, but I did do a two-dimensional geometry problem. But something from this list is going to be there, maybe even more than one thing from this list. So it'd be good to practice that. So this is a good example, and it's not very bad if you just know the framework of it. So what would be the first thing you'd want to do here? Right, find a matrix for this. This is a 3x3 system, right? So there's basically, you want to think of the system as being x prime equals ax. And in this case, the A is the matrix. What would be the matrix A?
Negative 3,
Negative 3, negative 1, negative 2.
1, 0, 1,
0, 1. And 1, 0, 0. Please double check that. Make sure you have it right, because if you're starting off with the wrong matrix, it's going to be very unpleasant. Right? So there's your matrix. Then the things that you need to really remember are that there's a Jordan canonical form for this matrix, which we call J. And what we do is